So this is Team Rehab, and we are doing EMG wrist sensing. So we worked with Motus Nova using the Hand Mentor device. It's an at-home rehabilitation device for stroke patients. So the idea is it can be donned using one hand and using the other hand for rehab. So as you can see, Julian in the video is using the Hand Mentor to control the base station and play a game, which gives repetitive motion and feedback so he can do rehab at home. So Motus Nova has FDA approval for the Hand Mentor. They're one of the only companies that has this, which means that the Hand Mentor can basically be rolled out to hospitals, to people's homes to provide rehab away from physical therapists and clinicians. One of the issues with the Hand Mentor is that it can't be used by those with really limited mobility. So stroke survivors that have only a couple degree range of motion or have very weak motion, it's a challenge for them because it relies on some physical movement sensors. So there's a bit of a lack of audience due to the sensors used currently. So our goal for the project is to classify the intent of a healthy normal user, and that's doing intent of movement up, down, or no movement at all. So the way we're going to classify that intent is by using EMG sensors. So that's electromyography. We'll be using sEMG, which is surface EMG. The reason why we're using these sensors is because we can look at what's going on in the muscle, not what's going on at the wrist. So for those stroke survivors that have a really limited range of motion, the wrist movement might not happen, or it might happen in a very small degree, but we can still look at what's going on in the muscles and try to gain an intent of what they're trying to do based on reading their muscular activity. So the classification problem is basically the meat of this project. How do you figure out what's going on with those muscles when you're trying to move up and down? So you're looking at two muscles when you're measuring wrist movements, the flexor carpi radialis and the extensor carpi radialis longus. So those are responsible for moving your wrist up and down. We're measuring these with two sensors. So we have a surface EMG on the top and the bottom of the arm, measuring these muscles respectively. So to do this, you must have no perceivable delay to the patient. It seems to be around 300 milliseconds at max. So with the classification problem, we're not looking to measure the degree of motion. We're looking to measure purely the intent of the motion. So if you have the derivative of position is acceleration, we're not looking at the position, we're looking at the movement. So up, down, or no movement at all. So when you're looking at these muscles, you're going to probably have both of them firing, especially if you're just holding still, or if you're moving up, you might see crosstalk between the two. So you have to take a modeling approach when you measure these EMG signals. You're not just measuring action potential or a threshold, you're looking at behavior.
Thanks for that overview of our project, Nick. This is Nate Weinberg, and this is a topology of our sEMG movement classification system. We're using two MyAware EMG sensors, and they're outputting an integrated, rectified, and enveloped analog signal. They allow for adjustable gains for comparable outputs across different people. In addition to the sEMG sensors, we're utilizing the angle sensor in the Hand Mentor, which outputs an analog voltage. Those signals are then sent to the MCP3208 ADC. This ADC is a Raspberry Pi hat that samples with 12-bit resolution at 100 kilosamples per second. It then outputs that data into the Raspberry Pi through SPI. We then capture that data through a Python script on the Raspberry Pi, which allows for time-synchronized sEMG data as well as our ankle data. This gives us the ability to directly correlate the positional angle data to the sEMG data. This is very useful for our classification phase. For classification, we use a neural network that classifies movement upwards, movement downwards, and no movement. It does this through binning the data into specified windows and using half of the previous window to aid in its classification. Had our project been able to proceed, we would have displayed the sEMG and ankle data graphing on a website as well as its current classification. In addition, we would have had the ability to send that data directly to Motus Nova through the base station to allow for further analytics to aid in clinical physical therapy.
I'm Julian Duran, part of Team Rehab, and I'll be talking about understanding the target muscles for our project. So when it comes working with EMG sensors, it's very important to understand the muscles that you'll be working with. There's many factors that have to be considered for the outputted signal. Let's say blood vessels, those affect the outputted signal. The neighboring muscles, they actually can affect the signal that we receive because of crosstalk. The fat between the muscle and the skin, if it's not making a clear contact with the muscle, there's obviously going to be some kind of distortion with our outputted signal. And the gain, we have to adjust it from person to person depending on the subcutaneous fat that each individual has. Other things that affect it are the hair. So if you have a lot of hair, it's probably recommended that you shave all your hair. That way the sEMG gets a clear contact to the muscle area that we are recording. And of course, EMF interference. So phones and any devices that release any kind of EMF interference, those should be kept far from the EMG sensors, just so that we can get the best outputted signal possible. So for our project, one of the muscles that we had to study was the flexor carpi radialis. So this is a thin muscle on the forearm that is responsible for the flexion of the wrist. It starts at the humerus and goes all the way down to your index finger. And we also have to consider any kind of nerves or blood vessels because, as I said before, those affect the signal. So for this muscle, the median nerve is the one that controls the muscle movement. And the blood vessel that runs through this muscle is the ulnar artery. So those are two major things that we have to consider when using our sEMGs, the median nerve and the ulnar artery. For the other muscle, we study the extensor carpi radialis longus. So this one also helps with the movement of the wrist and of the hand. And as the previous muscle, it starts at the humerus and goes down to the index finger. And for this one, the radial nerve and the radial artery are the ones that control the movement of the muscle and that supports the circulation of the blood. And so then we had to start looking into how should we place these EMG sensors on the individual muscles. Just from reading a lot of research papers, we discovered that it measures the activation of neurons that causes muscle contraction or relaxation, and that the electrodes, they should be placed on kind of like if you consider your muscle laying flat horizontal, it should be placed on a midline along that muscle so that you could get the best outputted signal. If you put it too edge of the muscle, then you're going to also read signals coming from the muscles around it, so that's considered crosstalk. And if you put it too close to either end of the muscle, then you're going to start reading the tendon instead of the actual muscle signals, which will cause for a weak signal.
Through reading a couple of research papers, we found that 1 centimeter was generally agreed to be a good distance to place the sEMG electrode pads apart from each other. We ended up using 2.5 centimeters, which is a little bit longer than expected due to the electrode pads we have being a little bit larger. This didn't seem to affect our signal very much and wasn't a problem. For reference node on the skin, the reference node basically acts as a ground for the surface EMGs, and the reference node needs to be placed on somewhere where there's no muscle activity when you're moving. So say you're moving your wrist, you wouldn't want to put the reference pad on the flexor or the extensor because that's what you're measuring. So you could use bicep, elbow. We actually found good results with the bicep because the skin on the elbow can be dry and that provides more interference between reference tissue and the surface electrode. So skin preparation is very important for surface EMG. We used alcohol to clean the skin and that removes any oil and skin residue. Again, you're trying to get rid of everything that would be impeding the signal. So we used gel pad electrodes. Surface EMG electrodes have a couple different types. There's a foam type, a gel pad type, various others. Gel pad ended up working the best for us. Also, you should shave the arm if there's a lot of hair or thick hair. Just generally with surface EMG, you're trying to make your life easier by removing anything between the electrode pad and the muscle, obviously without going beneath the skin. So for placing sensors, we read a bunch of research papers where researchers were doing similar things to us and using surface EMGs to measure various muscles. Through this, we found a couple similar ideas where people were using these muscle groups. So through those, we figured out a generalizable placement routine, and we made a placement document that would be used by somebody who's putting the surface EMG electrode pads on themselves. So you want to take a baseline measurement between the wrist skin fold and the elbow skin fold, and then from that we divide into fractions. The fractions make it generalizable. As far as us four, it worked for all of us, but the idea is that it would be generalizable for any patient. So for data capture, on the left you can see the hand mentor being used. Being graphed on the screen, you can see the hand position data as he moves his hand up and down, and you can see the EMG data. It's much more volatile, so that's again one of the reasons why you have to take a modeling approach to capturing EMG data and trying to gain intent out of it. And on the right, you can see me wearing the hand mentor with some electrodes hooked up and Noah basically making sure everything is going right. And adjacent to me is the data collection setup. So we have the Raspberry Pi, the ADC, the sensor boards themselves, and this is all running in a Python script doing data collection. So for part of our design, we had to make an enclosure. I did all the designing in SolidWorks, and we 3D printed in PLA, like pretty much anyone does with a 3D print. The box was comprised of basically three components. There was the main section with standoffs for the PCBs. There was the front plate, which has a cutout for the Jetson Nano, and a top plate, which has standoff mounts for the EMG sensors. And you can see those here as it's pieced together. It's held together with screws. All the holes were drilled in a drill press, so pretty manualized. I did that instead of printing the holes because the holes were coming out not totally circular, so I just drilled them myself instead.
In coordination with Nick, I was able to create a PCB that could fit inside his 3D printed enclosure or allow us to use the MyAware EMG sensors. We created our own PCB based on the MyAware PCB. I did that utilizing DipTrace, and it was a combination of two MyAware EMG sensors as well as two daughter boards that are required for the extension leads for the EMG sensors on our arm. We also integrated a 1K low pass filter that the MyAware boards don't include, so we added that along to our circuitry. It's also a two-layer board that allows for a 3.5mm jack input and output for the extension leads, amplifies the signal, integrates it, rectifies it. That allows for us to more easily capture it on a Raspberry Pi. The far right picture shows the schematic from DipTrace. The middle one in green shows a 3D rendering of a finished PCB, and the partially completed PCB is on the far left that we got from OSH Park. Also, in order to plot and show the user a more visually acceptable view of the sensor data that we're capturing through the EMG, I designed a web interface to both plot the GPIO data from the EMG sensors as well as pass along information from our Python script that would say if the muscle is moving up, down, or not. Unfortunately, due to campus closure, we weren't able to use the EMG sensors, so I relied on using an ultrasonic sensor that went through the GPIO of the Raspberry Pi that we would use for data collection. And I just passed along that data through the Python script, which was representative of sensor data that we would be sending from a Python script for data collection anyways. The web server was run in Python, and it utilized Flask for the API library, which allowed us to pass that GPIO data onto JavaScript, which allowed us to plot the information in a very configurable graphing interface, lets us pan, zoom, all those kinds of things through the data. And as you can see from the demo website, there's a line that says newest value near the middle, and it shows the current value that's being read in. And that spot would have been used to display the move up, move down, or node movement section. Originally, we had attempted to use Docker to create a website. Though Docker was incredibly useful, you could spin up an environment incredibly quick. The access to GPIO sensor data became quite difficult for passing that information through to the Docker container. And at the end of the day, it created more work than it originally saved, which is why we utilized a Python web server.
So when it came to data collection, what we had to go through was using healthy patients and attach the electrodes, the flexor and extensor muscles. For our case, we only had available to us our group, so the four of us, and we did this within multiple sessions, and we tried to keep it consistent in terms of the placement between one person to the another. So the way that we did this is, as Nick talked about earlier, we created a document that went over a procedure of measurements and taking fractions of those measurements of where the sensor should go on each person's arm. And so the data was windowed and it was hand labeled. We originally tried to do an automated labeling, but we couldn't get a right frame size in order to show the correct intent that the user was trying to do. So we decided that it was probably best to go with the hand label data. That way we know exactly what the intent of the user was, and we could use that for training our model. And so from the outputted data that we collected, a sliding window was created for the training data. And the window was 250 milliseconds by 3 sensors. Sampling rate was 1,000 hertz. So we used 3 sensors total, 2 sEMG sensors and 1 potentiometer to be able to show the intent of the user. The windows were hand labeled as we were collecting the data. So as we went through, we would tell whoever was wearing the device, move your wrist up. and we'd go in, label that frame as movement up, and then we'd repeat this process for movement down and no movement. We would switch between different starting angles. So we'd start with the farthest down possible that the device would allow for range of motion and move our way up. And then the next starting would be a little bit higher up and then a little bit higher. And that's pretty much how we did for all three of the different classifications. And through supervised learning, the algorithm uses the model to classify new input data. So we take in all this data that we collected and we use a portion of it as training data, and the other portion we then use it as test data. And Noah will go into more detail about this when he talks about the model.
I'm Noah. I worked on the machine learning portion of this project. So to reiterate our goal, we wanted to classify the intent of a healthy user who was using the Hand Mentor Pro to classify their wrist movement as moving up, moving down, or no movement. And so for a basic introduction to machine learning, we have our input data X and our output data Y, and the goal is to find the function that transforms that input data into the output data. And so the input to our algorithm is features. So these are individual characteristics of data that tell us information that will lead to the classifying of that input data. And so our features are the individual analog samples in our data windows. So one common approach to machine learning is a convolutional neural network, which is an algorithm that takes an input tensor, which would be our data window, and is able to abstract the features out from each layer of the network. So on the left side, the input to this convolutional neural network is a face, and as the neurons propagate through, features start to come out. So the second image shows the low-level features, which are lines that tell what kind of face this is, and as it propagates through, those features become high-level, and we get eyes and nose and mouth shapes, and then at the end, it outputs a probability that this face is Sarah. So that's the same approach we have with our input data windows and our three labels. After our data collection, we came out with this data set with our 4 healthy patients, our 2 EMG sensors, and our 1 angle sensor. And you can see the number of samples we have in the table. Around 46% of the data is the no movement class. A fast Fourier transform of the windows is appended to the input windows, and the fast Fourier transform is just a mathematical transformation, and it creates extra windows for us to use as inputs to our model. When we trained a model without the angle data, our average accuracy was 46%, which is the percent of the no movement class. So there was some kind of problem where the model wanted to classify everything as the majority class. But when we include that angle data, the accuracy is much better. And going back to our goal about classifying healthy patients, since this angle data is going to be available, it's fine for this model to include that data. And we plan on continuing this project with Professor Takesh and support from Motus Nova. And I personally want to continue working on this during my master's. And we want to see if we can build a model that doesn't use the angle data and has comparable results. So that would be good for applying this to the stroke patients. And that's the end.